So, welcome. As most of you may have heard, last week there's been a major breakthrough announced in fusion. And I wanted to take this as the opportunity to talk about my two favorite topics, fusion and international law, and to present my work that I've been doing for the last 9 months and hopefully will be doing for the next couple of years. This presentation will argue two things. And my first argument that I want to present is that fusion is a safe technology that will play a crucial role in our future's energy production. But first, what is fusion? So fusion is a nuclear technology. So nuclear, we need to look at the atom. The atom is the most fundamental Lego brick in the universe. So everything we know is made out of atoms, and an atom consists of a nucleus that is surrounded by electrons. So we take a look at the center, at the nucleus of an atom. And when we talk about nuclear and the energy that we can get from a nucleus, we mostly think of nuclear fission, because today's nuclear power plants, but also the majority of nuclear weapons work with nuclear fission. Fission, which is a process that happens in heavy nuclei. So, for example, uranium. You can use a heavy uranium atom, which is relatively heavy, and you can split it into two parts. And in that process, energy is released. However, what you can do also is use lighter atoms, such as hydrogen or helium, and fuse them together. And in that process, energy can be released as well. So today we know fission, we've got a heavy nucleus, we split it into two and we get energy. You can also use light nuclei, put them together and also get energy, and that is called fusion. However, there is a problem. We're doing fusion now for 60 years. About 6 years ago, fusion research has started, and until today, there is no functioning fusion power plant in the world. Why is that reason? One of the main reasons is that you need to heat your material to extremely high temperatures to make fusion happen. We're talking about 150 million degrees Celsius that are required on Earth. For example, the core of the sun is only about 15 million degrees hot. So we need 10 times hotter than the sun. By the way, that's the same process that happens within the sun. So with fusion, we're trying to build small suns here on Earth. And to reach these temperatures and to handle these temperatures, we need to get to a technology that's not really existing today, but we're working on it, and especially our society, the Max Planck Society, is working on it. One way to bottle your artificial sun is called magnetic confinement. So you see here, there's like donut-shaped machines that use magnetic fields to let your 115 million degrees hot plasma levitate. There's one at the Max Planck Institute of Plasma Physics in Garching, S6 Upgrade, where I've been working for about 2 years. And there's also a big machine, Wendelstein 7X, located in the northern part of Germany in Greifswald, which are Germany's most important fusion research machines. But there's also a different technology called inertial confinement or laser fusion. And this is what has been in the news last week. That's a picture of the National Ignition Facility located in the Lawrence Livermore National Laboratories in California in the United States. And there you can use lasers to initiate your fusion process. Within Europe, we're doing fusion because we want a clean energy source. Because this bottle of water contains about roughly the same energy as an entire train full with coal. So the potential of fusion is enormous. Just think about how big a train with coal is, sometimes kilometers long, 1 or 2 kilometers, the same energy as in just a bottle of water. So the potential is enormous. But how do we get there? When will we finally have electricity coming from these fusion reactions? So the European research laboratories formulated a roadmap which tries to get us to the goal of fusion energy. Today, we've got the facilities that I've just showed you, and currently in southern France, there's a project under construction called ITER. ITER is an international organization that builds a big machine that's plan is to show that the fusion reactions within magnetic confinement, so the first kind of fusion, is possible. The plan is that by 2035, the machine is in a specific mode of operation to show that this technology is feasible to follow. After that, our plan within Europe is to build a demonstration power plant, because even though if there's more energy produced than put in the reaction, you still need to convert that energy into electricity, because that's what we need at the end. And this is planned to be built in the 2040s. And once that is shown that it's working, then the plan within Europe is to commercialize fusion in large scales. However, now there's a big question mark if we can speed it up due to what has happened last week, or what has been announced last week, and what happened, I think, 2 weeks ago. And that is, for the first time ever, after 60 years of research, fusion produced more energy than it was required to heat up the process in the beginning. So what they did at the NIF, the National Ignition Facility, put 2 megajoule energy of laser energy into a small target, and about 3 megajoules of energy has been produced within the target. So there's a 50% energy gain. An energy gain has never been reached before, and even the first time it has been reached was even a 50% energy gain, and not just like, I don't know, 1 or 2%. So this is a very big news for fusion. However, is fusion close? Yes and no. So there's still different things that need to be accomplished before we're having a fusion power plant. First, we need to produce more energy than is put into consistently. We needed 60 years to make it happen for the first time. Also, the NIF was operational for more than a decade before we were able to produce energy. Also, it needs to be done several times per second. That's the aim, and not like once every, I don't know, couple of weeks, what is now planned at the NIF. Second, I talked about a 50% energy gain that has been accomplished. There needs to be even bigger increases, because the laser had 2 megajoules at the target where the energy was put into the fusion material. But to produce the 2 megajoule energy of laser, you needed to put 200 megajoules originally. So in the end, the energy gain is less than 1%. So there's a lot of areas where you still need to optimize the technology. And at the end, you still need to transform the energy that is produced into electricity. To the question, when is fusion ready, there are different answers. Again, within the European Union, maybe in 50 years. If you ask some American startups, it can be ready in 2024. There's one company that's promising, but the chances are likely that 2030s is a time frame where we're maybe getting fusion energy out of the grid. But now, what does it mean for international law? Even though fusion poses some challenges to international law, they are surmountable. They exist, but they're not too big to handle. Today, I want to focus on 3 areas of international law. They are environmental law, space law, and nuclear law. So they're not the classic fields of international law, but they're very, very interesting questions that are raised by fusion in these areas. So again, why are we doing fusion? We want a clean energy source. And clean energy, of course, is extremely important, because between 80 and 90% of all greenhouse gas emissions can be related to energy and energy production. I've brought you an excerpt from the Sharm el-Sheikh implementation plan, which was adopted at COP27 1 month ago, where the need for sustainable energy was reiterated. The IPCC, the International Panel on Climate Change, tells us we need to peak our emissions before 2030. So this raises the question, can fusion help with that regard? Maybe not, but for our long-term goals, limiting the heating of the world to 1.5 degrees, or to achieving net zero by 2050, fusion can play a significant role. Also, when we're talking about a nuclear technology, the first question that's always raised is what about the waste? One of the big problems with fission is the waste. Fission produces waste that is radioactive for hundreds of thousands of years. What is it with fusion? I'm not going to lie, fusion is going to produce waste as well. That waste is going to be radioactive, but, and that's the big difference, only for around 100 years. And 100 years of waste is a time frame that is quite manageable for humanity. If we think about plastic, how long it takes plastic to dissolve, that we are in the range of a couple of 100 years. So 100 years as a time frame for waste, I think is quite acceptable. But of course, the waste is going to pose some legal problems how to deal with that radioactive waste. And a different topic is the material that is used for fusion. One material that is going to be used is tritium. Tritium is a hydrogen isotope, but it is both radioactive and almost existing on Earth. So first, you have the radioactive material, and that radioactive material needs some kind of handling because of the hazardous effects that it can have to the environment. And since tritium is almost not abundant on Earth, you need to produce it. And the easiest way to produce tritium, apart from fission reactors, which we're planning on not to use in the future, is from lithium. And I'm sure many of you have heard that lithium is currently harvested under conditions that are very, very bad for the environment, especially if we take a look at Bolivia. So this is a question that somehow needs to be dealt with also on a level of environmental law. The next point is space law. I just mentioned a company that wants to commercialize fusion in 2024, so in about a year's time. They're planning to use helium-3. Helium-3 again is an isotope, so a special kind of helium. The normal helium that we know is helium-4, but they are planning to use helium-3. Helium-3 poses a lot of advantages within fusion. However, there's very big problem. Helium-3 is also non-existent on Earth, and it's quite difficult to produce. It can be produced, but also with a lot of energy required, and it's not clear if there's a method to produce enough helium-3 for fusion. But there is a place, not on Earth, but in space, where we can get helium-3 from, and that is the moon. The moon has huge resources of helium-3. And for the first time in decades, the question of the commercialization of the moon becomes apparent. And for that, there's the Moon Agreement of 1984. And the Moon Agreement has a significant provision, which is Article 11, which states that the moon and its natural resources are the common heritage of mankind, and that it cannot be the property of any state or non-state entity.
Is the US a party to that? No.
Yes, they are.
US is a party?
I think so, yeah. And
United States.
And what is going to become very interesting for international lawyers is Article 11, paragraph 5, which states that there should be an international regime to govern the exploration and exploitation of natural resources on the moon, as such exploitation is about to become feasible. And if we take a look at the progress that SpaceX has been made within the last years, maybe the exploitation of the moon's resources is about to become feasible. So this is going to be a very interesting topic in the next decade or two, to establish that international regime to govern the exploitation of natural resources. And finally, topic where I've been working. It's not? Okay. Sorry.
Neither Russia nor China.
Okay. Okay. But there is a UNGA resolution endorsing that agreement. Yeah. And this is where the discussion of instant customary law comes from. Yeah. Now about the last part of international law, what I want to talk about is nuclear law. For those of you who have attended my last Monday meeting, you're familiar with the 4 pillars of nuclear law. They are safety, security, safeguards, and civil liability for nuclear damages. So what is safety? Safety means to keep the environment and the people safe from the hazards of nuclear activities. Security means to keep the nuclear material and nuclear facilities safe from external influences. Safeguards is everything that is related to the non-proliferation regimes, so to keep sure that a non-nuclear weapon state remains a non-nuclear weapon state and doesn't acquire any kind of nuclear weapons. And there's also a special regime for nuclear for civil liability in the case of a nuclear accident because of the high sums that can follow from a um, nuclear accident. So speaking of safety, fusion is a very safe technology. The big fear of fission of current nuclear power plants is the worst case scenario of a meltdown within the core of an uncontrolled chain reaction. Things like that cannot happen in fusion because fusion requires a constant input of heating and a constant input of new fuel. And once that is shut down, the entire facility stops working. So there's no risk of an uncontrolled chain reaction. And even if there is some kind of accident, the amount of radioactive material that could be introduced into the atmosphere is so small that only very local communities directly next to a power plant could may be affected, depending on the size of the machine. The part that raises some kinds of concern and where some kind of response from the international law side has to be produced is the safeguards pillar, because NIF, the facility in the US that has reached ignition, is not a peaceful facility. NIF wasn't built to achieve fusion energy. NIF was built to test nuclear weapons. Or rather, you cannot test nuclear weapons like we did to a couple of decades ago. Today, nuclear weapons are tested by computer simulations. But how do you know if a computer simulation works? You need to test these codes, and they are tested at NIF. I can also read out some quotes from the press release, which shows the significance of the priorities within NIF. The US Department of Energy announced the achievement of fusion ignition, blah, blah, which will pave the way for advancements in national defense and the future of clean power. This first of its kind feat will provide unprecedented capabilities to support NNSA's stockpile stewardship program, so which is again a nuclear weapons program, and will provide invaluable insights into the prospects of clean fusion energy. So as fission, fusion poses some kind of proliferation risk as well. They exist, but compared to fission, they're extremely lower and also mainly attributed to this one kind of laser fusion. The European followed approach by magnetic fusion is, from a proliferation point of view, way safer. But again, fission is way more dangerous from a proliferation point of view, and we have found a way with the non-proliferation regime, with the safeguards regime from the IAEA, to tackle these issues. So I'm sure that our work as international lawyers will find a way to also find a way of nuclear fusion that makes it safe and does not provoke any kind of nuclear weapon responses. So to reiterate my arguments that I've made, again, fusion is a safe technology. It's going to play a crucial part in the future energy production, and it poses some kind of questions to international law, but these questions are surmountable. With that, I want to thank you for your attention.